Good afternoon and welcome to NASA's Jet Propulsion Laboratory. We're having a fabulous day here. We've had a very successful flyby of Comet Hartley 2 by the recycled Deep Impact spacecraft, which is part of the EPOXI mission. And we have a panel here that's going to tell you about some of those early images and what they've been able to discern from them so far. I'll introduce our panelists to you. First, we have Dr. Charles Alachi. He is the director of the Jet Propulsion Laboratory. Next will be Dr. Ed Weiler. He is the NASA's Associate Administrator for the Science Mission Directorate. Tim Larson, he is the Project Manager for the EPOXI mission from the Jet Propulsion Laboratory. Dr. Mike Ahern, he is the Principal Investigator of the mission, and he is from the University of Maryland. And finally, we'll hear from Dr. Jessica Sunshine. She is the Deputy Principal Investigator, and she is also from the University of Maryland. And we're going to begin with Dr. Alachi.
Well, good afternoon. As you could imagine, this has been a great day for NASA, for JPL, for University of Maryland, for Ball Aerospace, and for our nation quest in exploration and discovery. And I'm particularly proud of the EPOXI team, which really made this look like it's an easy thing, to do. Well, in reality, these are always very challenging activity. I thought, just in case you forgot how it was exciting this morning during the encounter, we have about a 30-second video. It seemed like it had been a long day. A 30-second video to show you how it was in the mission operation room.
All right, our first image from closest approach has been saved to our file system. You can see we're all staring at the screen waiting for our software to pick up that image and display it.
Congratulations on a fantastic flyby. Good job, everybody.
You see how easy they make it look like? Now, before I introduce the next speaker, we are very, very honored today to have also with us, as you saw in the picture here, Mr. and Mrs. Malcolm Hartley, after whom the comet is named. Malcolm and Mrs. Hartley, do you mind standing up so we can... Okay, now I would like to introduce the next speaker, Dr. Ed Weiler, who really make all of this thing happen. Ed?
Oh, I was reacting to that comment. It takes a village, Charles. Good morning, or good afternoon, actually. I was in that room, and I'm going to say a few things about the human experience that was for me. But I just wanted to point out that I selected Deep Impact, must have been about 10 years ago now, to go to, it had a rather interesting idea. It was going to carry a copper bullet about 200 pounds and blast it into a comet, and to understand what the comet was made out of. Somehow this survived peer review, luckily, and we selected it. Little did I know back in 2000 or 1999, I forget the exact year, that I'd be sitting here today talking about a second use of that spacecraft, and a really darn good bargain. The original Deep Impact mission was about $260 million, and then Mike Ahern and his other people at Maryland and other universities came up with the idea of, we've had a successful Deep Impact mission. There's enough fuel on this satellite to go to other places, in fact, a specific comet, namely Hartley 2, and they made a proposal and for reusing this used satellite, and we accepted it. And today is the culmination of that. For about $45 million, we got a full-up discovery mission, which is, in today's dollars is probably worth $300 or $350. So for about 10% of the cost of a discovery mission, we got a second discovery mission from the same spacecraft. I'd like to do that again. We're going to be looking at other satellites, how we can do this again. In these days of hard economic times, this is a really good deal. In terms of the human experience, I remember the seconds before the image came down, and I thought to myself, this is an exploration moment in the following sense. Here we are sitting in this little building in JPL, and we're going to see something that no other humans in the history of humankind have seen. you know, the nucleus of Hartley 2. And then it came up, and it was incredible. It was cigar-shaped. When I was growing up in astronomy, we thought comets should be more or less uniform, and every time we look at something, we find out our textbooks were wrong. This is what science is all about, and I'd like to use the remaining minute I have here to talk about what this should mean. I have kids, many people in this room have kids. We have a generation of kids growing up playing with computers and video games and living in virtual reality. They blow up comets, they blow up planets, they do all these great things on the computer, but it's all virtual. I'm hoping a few kids were watching today, and if you were, please understand this message. What you saw today wasn't virtual, it wasn't a computer simulation, it was real. It was the Earth seeing this comet close up for the first time in history. That's fun. Science can be fun, just as much fun as a computer game, but probably a lot more important to our society. Thank you.
Thanks, Ed. As has been mentioned, this EPOXI mission is a bonus mission using the Deep Impact spacecraft. If you count the Temple 1 encounter 5 years ago and the extrasolar planet observations that we did on the way to Hartley 2 and now this encounter, it's really been 3 missions that the spacecraft has accomplished. And this morning, I think everybody on the team felt really absolutely privileged to be part of an event like this. On the way here, we traveled about 2.9 billion miles, so that was quite a road trip. We had 3 Earth flybys. We took advantage of the gravity assist on these flybys to adjust our trajectory just enough so that we could get out to the comet. And starting with Temple 1 and then now finishing with Hartley 2, 2 comet encounters for the spacecraft. I'd like to point out the contributions of some really fantastic people because you can't get this done without an excellent team in place. And we had a spacecraft team that was comprised of JPL engineers operating the spacecraft and engineers from Ball Aerospace operating as well. And I do want to thank several of you are in the audience today, and I want to thank all of you for your participation and the hard work that you did. It looks easy when it comes to this point, but it's the end result of a tremendous amount of work. And all the testing, all the sequence design, all the reviews and risk analysis, everything that we've done along the way pays off at moments like this. So thank all of you. And then, of course, supporting an international science team with folks from all around the world who are involved in interpreting these results and putting all these puzzles together. So this has just been an absolute blast getting here. In terms of mission events, we started observing the comet back on September 5th. The very first day that we pointed our cameras at the comet and took images, the comet was right there in the middle. So it was great to see that from the very beginning. We've been imaging almost continually since then. We took a break of about 4 days to cool down the IR instrument and to perform a calibration of the instruments and a trajectory correction maneuver. And then we started imaging again. Since October 1st, it's been nonstop imaging of this comet. And that has generated a lot of interesting data along the way for the science team to start chewing on. And very early on, we discovered some very, very interesting behavior and unusual behavior for this comet. Until a few days ago, we didn't really know what this comet nucleus was going to look like. I didn't have any idea what kind of shape it would be. And thanks to the work from the Arecibo Radar Observatory, that gave us some of the first clues of what we might be looking at. If you roll that video, you'll see a compilation of images that have been turned into a movie of this comet as seen by the Arecibo Radar Observatory. And that gave us a very first glimpse last week into what we might be approaching. As we got these images, seeing this very elongated body, we started scratching our heads again and looking at our AutoNav software all over again to make sure that we didn't have any problems posed to the performance of the AutoNav software. This is a software that keeps us pointed at the comet all the way through the flyby. And it was a little different use this time on Temple 1. We stopped at a certain point and stayed in the shield mode. This time we tracked the comet all the way across. So we knew that it would be a little bit more of a challenge than the last time we used it. But there had been a lot of testing, a lot of simulation done along the way to be sure that it could handle all kinds of different comet situations and comet shapes. And so it was gratifying to see that it worked really well. In terms of today's flyby, we couldn't have asked for a better performance from the spacecraft and from our navigation team. We were exactly where we wanted to be. We were within 2 seconds of our flyby time, which was exactly within the capabilities of our imaging sequences and keeping up with everything. We were at 700 kilometers. That's what we aimed for, and we were just about. Our miss distance was still about 700 kilometers, just about 3 kilometers over to the side, and so that was absolutely fantastic performance in terms of navigating and getting there. And our flyby velocity ended up being in the vicinity of 27,000 miles per hour. So this thing came by very, very fast. It was a huge moment for our team. We were trying to think, what are the key transitions, the key moments going to be for the team that tell us that this was successful? And one of the first ones, we knew that at the approximate time that flyby would occur, because that was in the plan, and it's all set by the trajectory as we approach. But one of our key things that we were looking for is getting the signal back from the high gain antenna. When we switched from the low gain to the high gain and seeing that signal come back, that was a big sigh of relief for us. We knew that we had survived the trip, and we were ready to finish everything off. And if you show this image on the screen here, you'll see that when that first image came down showing the comet in the field of view as we were approaching it, even though it was a distant image of the comet, very small, and we knew that we were there. We knew that we'd pointed in the right places, we knew that we'd got what we wanted, and that everything else that would be coming down would be exactly what we'd been looking for. And it was hugely gratifying to see this happen. In terms of where we go from here, we're going to spend about 3 weeks imaging the comet as we go away from it. So we'll get a lot of departure sampling of the comet to add to the data we've already collected. And then we'll perform one final calibration of the instruments to help with the science data analysis. And then after that, we'll await further instructions from NASA. So with that, I'll pass it on to Mike.
Thanks, Tim. The first thing everyone wants to know about the scientific return from a mission is how much it's increased our knowledge. But of course, the scientific work is just beginning now. The engineers did a fantastic job of getting us data. Now we have to make sense of it to advance the science. But from looking at the data we have, I am convinced that Comet Hartley will have increased our knowledge of how comets work by at least 3 Hartleys. The Hartley is a real unit of information, and 3 Hartleys is about a factor of 10. So the first slide, the first movie rather, the video that should come up, shows you observations we took on approach to the comet. So we had results even before we got there. And you see a movie in which the comet is brightening and getting fainter, and you see what looks like jets sweeping around. So we think, even then, we thought we probably had an elongated nucleus spinning around like this. And every time the active area gets into sunlight, which is over there, Charles Alachi is the sun, the jet gets active and spews out material, and you're seeing it sweeping out. And we already knew from looking at that it's not just simple rotation. It's probably doing this as well, or maybe doing this, and maybe doing this, all on top of that. It's a very complex motion. And that's why the jets don't repeat every time you see them. Each time you go through, they're a little bit different. So finding those jets on the way in was great. But the next thing we found on the way in was the chemistry that's driving those jets. And the next still picture shows a whole series of pictures over 2 days in light that's been specially filtered just to show carbon dioxide, dry ice in the nucleus that's evaporated and come out. Mostly what we think of as coming out of comets is water from ordinary water ice. The dry ice goes up and down in brightness dramatically. You can see in that picture how it goes up and down from October 31st to November 2nd. You can even see that it moves a little bit. When it's really bright, it's a little closer to the sun than when it's faint. The sun in this picture is up. So that was a great clue that we had a really interesting discovery. And the next slide shows that just 3 pictures, when the comet is faint on the left, when it's medium brightness on the right, and when it's really bright on the right. I'm sorry, medium brightness in the middle and really bright on the right. The top row is just the light of the carbon dioxide. So that's where the dry ice is evaporating. And the bottom picture is visible light. That's mostly the solid grains. So this says that there is one area in the comet that is incredibly rich in dry ice, and that's what drags out the grains and produces all of the phenomena that we see. Traditionally, we've thought that it was excess water driving these jets. This is a pretty clear demonstration that it's really extra dry ice somewhere close below the surface that's driving these jets. So that was one of our great discoveries on the way in, but that was before we had a picture of the comet. So now I'm going to hand it over to Jessica, who will tell you about the pictures of the nucleus and actually show you where we think that dry ice came from.
Thanks, Mike. Well, I know we all had a great treat this morning. We got to see a spectacular set of images, and I first wanted to start with showing you the 5 images we took nearest closest approach. Thank you. And they progress in this montage from the upper left clockwise down to the lower left. And what you're seeing is the images as the spacecraft took as it approached Hartley 2, went underneath, and continued to take images looking back. So we had quite a range of perspectives across this. And at this point, maybe it's the right thing to do is just stop and look at this spectacular comet. Mr. Hartley's comet over here, there's not much to say that you can say besides it's just amazing. However, they wanted me to say something. So we spent the last few hours trying to get some preliminary sense of what we think is going on the comet, which I'm going to share with you in a minute, and try to see how it relates to what we've been studying, as Mike talked about in the coma, the comet's atmosphere. So if I could have the next image. Let's see where Hartley 2 fits in our family portrait of comets. We've seen 5 others before with spacecraft. And you can see that it's actually quite small. That's the actual size is the little box in the lower right. We've blown it up so you can see it on a relative size. And while it's the smallest, no question about it, I think it's undoubtedly the most interesting, and for its size is the most active. And what we've been able to do with this mission is, for the first time, see jets going all the way to the surface and have a camera that's good enough to actually see the variability of the surface at the same time. And what we're working on is trying to link those two. That is, how does the activity that's natural to the comet affect its surface? So if I could have the next one, please. So here's a blow-up of the highest resolution we have so far. The comet is 1.25 miles in the long axis in this image. That's roughly the distance in Washington, D.C. from the U.S. Capitol to the Washington Monument, your average rally on the mall there. And you can see the dominant geologic signatures that we have 2 rough ends and a smooth middle. I'm not sure what that makes it, but that's what it is. And what we see is that where the activity is, where the jets are, is the rough areas. In particular, if you look on the sun is still towards Charles. No, actually, it's over here now on the right. Sorry, I got flipped around. But this is the sun side, and that's the rough area, and we're fairly confident at this point that that is, in fact, the end of the nucleus, the right end of the nucleus, that is rotating in and out as we've been watching it all these weeks, and in fact is where the dominant CO2 and what we now think is the dominant dust is coming from. And you'll see in a few images later that there are also jets on the other end, but what we're seeing is that we have rough terrain where the jets are, and in fact, in many cases, they seem to be correlated to specific topographic features. And the middle, in our best current interpretation, we think is material, fine-grained material, that has been redistributed across the comet and collected in a topographic low. And so you get fine, smooth material in the middle, in that low. We also found places where there are clumps of material. They appear bright here. I don't know if you can see the one along the upper edge, but you can see it sticking off the edge of the limb of the nucleus. And we think that those might be materials that are remnants of activity, that material that stayed behind, whether as other materials were ejected or moved by the jets around. So let's see. So let's go to the next image, if you will, and I promised to show you the other end, and this is it. This is enhanced, but it's still one image. It's the same exposure you saw before. We just stretched it a bit to show you the jets. And what's fascinating about this image is not only do we have major activity towards the bottom, but you'll see on the terminator, that is the line between the sun and the darkness, there's a line of jets which are illuminating the nucleus so we can see the full extent and silhouette of the nucleus. And we also see jets along that edge as well. So we have jets in the nighttime, we have jets along the edge, and we have jets in the sun. And this is probably as good a place as any to admit that we have a lot of work to do to try to understand what's going on here. But this is just spectacular. I certainly would personally like to thank everybody on the project. And we'll start rolling that movie of the 5 images again, and I'll send it back to Veronica.
Okay, I'm going to see if they're going to, give them 1 second there. There we go. Here comes our images in order. All right. Great job. Wonderful. Okay, we are going to now take questions from here in the Von Karman Auditorium from news media who may have questions, and then we will take some by phone. Is there anyone here in the auditorium, first of all, who has a question? If there's no question here, we can go ahead and take the call from Kennedy Space Center if they're ready.
And Kramer
All
for
right.
Spaceflight Magazine and the Planetary Society. I wonder if you could talk a little bit more about the smooth area in the middle. Could this be due to any melting at all?
No, I don't think so. Our best guess at the moment, and slightly more than a guess, is that it is in fact redistribution of materials. We've seen it in other places, other asteroids. Asteroids, for example, several have these kinds of features.
Okay, let's take one more.
Okay, and when do you expect to get some spectral data that you can release?
Well, I can personally say, as the person who tends to lead the IR spectral team, I haven't seen any yet because we've been busy. So we have released the approach data, and as we get stuff, we haven't even looked at it yet. So it's hard to predict when we'll know what's going on.
All right, I'm going to take one more by phone, and then we'll come back to you.
Be able to judge?
Okay, we're going to go to Amina Khan from the Los Angeles Times next.
Hi there, just wanted to see, sorry about that, looks like it got cut off. Wanted to see if there were any other plans for using the spacecraft to take a look at other comets.
I'll take that, this is Ed Weiler. We are currently in the middle of what we call an RFI, Request for Information. We sent one out a few months ago, I guess, asking the scientific community, do you have any ideas of what this spacecraft might be used for? It does not have enough fuel left, regretfully, to actually go through another encounter phase, that is, change its orbit and go to another comet or asteroid. But it does have enough fuel to maintain its attitude, etc. And it does have cameras and star trackers, which could be used for finding asteroids or doing astronomy. So we've asked the community to come up with ideas, and we'll be entertaining those ideas over the next few months and make some decisions. But what I do know is it doesn't cost a lot to use a satellite the second, third, or even fourth time. So we're looking forward to getting some good, unique ideas.
Okay, on the phone line now we have Tracy Watson from AOL News, and after Tracy's question, we will come here to Von Karman to take a question. Go ahead, Tracy.
Thank you. I just sure I understand this smooth middle. The valley then, and dust living in the valley?
More or less, yes. We don't know exactly how deep it is yet. We haven't gotten our stereo data yet, but that's the idea.
Okay, and are you surprised by the jets
a different place. This makes clear we have a lot of, if you could elaborate that.
I didn't catch that.
Were you surprised about the number of jets, and would you elaborate on that phenomenon?
Yeah, I'll take that. This is Mike Ahern. We've seen jets from the ground, not anywhere near the nucleus, but we know that many comets produce jets of material, and this comet in particular has been producing jets that ground-based observers have seen for a couple of months. So we were not surprised at the existence of the jets. We've known from close flybys, for example, of Halley, that there are numerous jets in some comets, not all comets, but the surprising thing was that for the first time we can probably track those jets really to individual topographic features on the nucleus, and that was the real surprise, that the brightness is sufficient to do that.
Okay, we're going to bring it over here to Emily Lakdawala, and you want to state your organization, and okay, you've got the mic.
It's Emily Lakdawala with the Planetary Society. Should we be surprised that there are jets coming out of the night side of the comet, or is that common with comets? Also, I'm wondering if, with the level of activity, how much longer this comet can remain so active before it burns out?
Okay, I'll take that one also. There have been indications from previous flybys of comets that there were jets coming from the night side, but this is by far the clearest demonstration of that fact. The rate of loss of material and how soon the comet will die depends on how they die, and we still haven't quite answered that question. Do they die by sealing in the gas, sealing in the ices, or do they die by running out of ice? This comet probably loses at least 1 meter to 1.5 meters of material on average everywhere on the surface every time it comes by the sun. So you can take the narrow dimension of 500 meters and at 1.5 meters per perihelion passages, it won't be around very long.
And then also I'm wondering about the HRI images and what the status on those is.
The HRI images are still being processed. We have to deconvolve them because that camera is out of focus. We know how to do that. Preliminary deconvolution still shows some artifacts. It's easy to introduce artifacts when you try to deconvolve an image that's out of focus, and the preliminary images still show that. I hope that we will have good images in the near future from the HRI.
Okay, we're going to take one over here on the other side. Stand by 1 second. Is that microphone on?
Alicia Chang from the Associated Press. Besides the difference in size and jet activity, what other differences have you been able to glean about Hartley 2 compared with the other 4 comets that have been imaged up close?
Well, the clumps that I referred to are something that was quite a surprise that we didn't expect to see, and we certainly haven't seen them elsewhere, even though we looked for them on Temple, for example. I think the surprises are yet to come on the compositional side because we haven't looked at the infrared spectrometer. The signatures in the fact that it was active was known, but I don't think any of us really felt we were going to see as much spectral signature as we did to produce the kinds of maps that Mike showed you. I don't know if you want to add anything.
No, we already announced a few weeks ago one way in which this comet's very different from others, and that was that it released in September, over a period of 2 weeks, a few million tons of cyanogen radicals. We don't know what those come from, probably from hydrogen cyanide, and if water did the same thing, we're talking 1,000 times more material without dragging out any dust. I just showed you pictures that show how when the dry ice gets active, you drag out dust with it, or solid grains. They may be water ice grains for all we know, but you drag out grains, and normally when the gas flows out, it drags all the solid material with it. This activity in September didn't do that. That is a phenomenon we haven't seen before also. So there are phenomena that we haven't seen before, and just like the clumps on the nucleus, we don't understand them yet.
I should say there are things on the nucleus that are familiar. We see in different comets little pieces of things that kind of are familiar, but putting it together is still something we're struggling with. It's a little soon.
All right, next we're going to go back to the phone lines. We're going to Richard Kerr from Science Magazine. Go ahead.
Thank you. I was just wondering about the CO2 dominance. Does CO2 dominate gases coming off the comet as a whole? What about the water? Is it the water normally the primary driver on other comets?
On most comets, the overall outgassing is indeed mostly water, and anywhere from 1% to 10% carbon monoxide. There are virtually no measurements of carbon dioxide except our own measurements at Comet Tempel 1 and one or two measurements from infrared spacecraft in Earth orbit. But probably it's of order 5 or 10% typically. We do not yet have a proper absolute calibration of our infrared spectra. We see the water there, but the water does not go up and down nearly as much as the carbon dioxide does when the nucleus rotates around and you get this big burst of carbon dioxide. You may get a very small increase in water. So in this case, we think this carbon dioxide, the dry ice, is driving it, but we don't have an absolute number even in the dry ice-rich portion.
Okay, thank you.
All right, the next call is from Jim Roop of CNN Radio. Please go ahead.
Hi, thank you, and congratulations, everybody. If you could help me here from the perspective of a regular member of the public, what specifically is the reason or was the reason for this mission? Is it because Hartley 2 presented itself as for an exploratory mission? Or is there something specific about this mission? And number two, why should I care as a member of the public? What impact does this have for me?
Let me try to answer the second one first.
Help me here from the perspective of a regular member of the public. What specifically is the reason or was the reason for this mission?
Can I go ahead and answer it? I think I know what he asked. The reason we wanted to go to Hartley 2 specifically is because it was a very small, very active comet and was therefore different from the other comets we had studied in detail. So that was the driver for choosing Comet Hartley 2 versus some other comet. What we hoped to do was to use the difference between a small active comet and a large, relatively inactive comet like Tempel 1 or Borrelly, to address the question of what parts of comets are due to the recent processing and what parts tell us about the formation of the solar system 4.5 billion years ago. And ultimately, what we want to use this for is to figure out how did we get here? What materials came to Earth 4.5 billion years ago that enabled life to exist here? What were the conditions when the planets were forming? The comets are the cores of Jupiter, Saturn, Uranus, and Neptune. They have large cores that are made up of comets. And the comets that didn't get captured into those planets are what are left over for us to see. So that's the ultimate goal in studying any comets. And the specific goal was to find one that is very different in its aspects than the ones we'd been to before.
Okay, next call is Stephen Clark from Spaceflight Now.
Hi, thanks for taking my call. Two questions. First, what does the shape of this comet, the elongated peanut shape, what could that tell you about its history? I mean, could it be like a rubble pile type comet like we see in asteroids? And secondly, When does the EPOXI project money run out, and do you have any plans for decommissioning? Thank you.
You get the first half.
Well, I was going to hope you'd do the second one. Give me a chance to think.
Well, I'll go ahead and address the second one.
There you go.
We're currently slated to conclude our current phase of operations at the end of this year, and so that's the current set of plans with the spacecraft. And like Ed mentioned a little while ago, NASA is looking at future uses, but that won't be decided yet for a little while.
So spuds in space is always a good analogy to small bodies. We've got potato shapes and all sorts of things, both in the asteroid and comet communities, but I think they're very different. The rubble piles are probably a lot stronger than anything we see inside comets. So the shape is telling us something. I don't think we have a clue yet what it is, and in fact, we probably have some arguments as to what it might be today, and we'll be working that over the next few months.
Okay, we're going to go to Wayne Friedman on the line next. Go ahead.
Congratulations on your work. Simple question for an average viewer out here. Can you give us an indication of the size, the temperature, maybe the pressures of those jets if a person were to stand next to them, for instance?
It would definitely be less than a fire hose, even though the jets behave much like the water coming out of a fire hose. You would feel it. It probably would not be enough to lift you off the surface, but it might. It's sort of on the borderline of being able to lift you off the surface.
But it doesn't take much to lift off the surface.
Yeah, you have to remember that the gravity is almost zero.
We're going to go again back to Amina Khan from the Los Angeles Times. Please go ahead.
Hi. I just wanted to see if the jets of the cyanogen, I think called cyanogen radicals, is that common? I mean, did those materials tell us anything about anything unique about this particular comet? And I know it's a little bit early to say, but has what we've learned thus far over the past several weeks told us anything new about the origins and development of our solar system?
Trying to interpret any of the data from a fast flyby in terms of the ultimate origins question will invariably takes a lot longer than the flyby. The engineers come along and they give us these wonderful data, and they dump a ton of information on us, and sorting it all out in terms of origins will take years.
Cyanogen.
Oh, I'm sorry. The cyanogen jets in particular, the most useful thing we think at the moment will be in relating them to the jets we see here and using the combination of the two to figure out exactly how the nucleus is rotating, because the nucleus rotates over something like 18 hours, and the spacecraft flies by, and all our images of the nucleus that you have seen were taken in a period of roughly 200 seconds. So the nucleus doesn't move enough for us to see the rotation. So combining the data on the jets from two different directions, from the spacecraft and from the Earth, is the only way we'll be able to sort out what the actual rotation is.
All right, we have two callers at Kennedy Space Center. Would one of you please go ahead and please give us your name and affiliation?
TK Meunier, Denver Daily News. Back to the hand bone structure. I guess I'm asking for speculation. Could centrifugal force cause your idea that that's fine grain in the valley areas or the center area? And would that be more prone to fracture and break the comet into two, or would the fine grain make it even more stable so that it would outgas only on the ends
Well, there's a lot of speculation in there. I think if the centripetal force was an issue, the thing would have broken apart a long time ago, because we don't think the comets are very strong. And the rest, I think, we'll put it in the list of things we're all thinking about as ideas. Honestly, we just don't know at this point.
I'll speculate that if the torque from the jets were to spin up the rotation, and the rotation does seem to be changing, although it seems to be slowing down. If it were to spin up the rotation so that it were going around in a few hours, then I'm almost certain that in fact the two pieces would fly apart right at that neck.
All right, let's go
Sean
ahead.
Sullivan, Aiken Standard. I saw the graph of the brightness variation during the approach. Is that directional, like a surface feature, or would that be seen from all directions, like a dust cloud? And what was the phasing of the encounter relative to that up and down motion?
The brightness fluctuations are associated almost entirely with jets that start out pointing very nearly towards the sun, at least as seen in projection on the sky from the spacecraft. Now, they may be tilted behind the plane of the sky or out from the plane of the sky, but pointing more or less towards the sun. And then they rotate around. So it's almost certainly a relatively small fraction of the surface that's producing them just to keep all of the material going in one direction. Working out the details of where it is, Jessica showed you roughly where on the nucleus we think all that activity is happening. It's on the end where you see the jets in the picture that's up right at the moment. But beyond that, I think we'd be speculating beyond the ability of our data at the moment.
Okay, on the line right now we have Mike Wall from space.com. Go ahead, please.
Sure, yeah. I would just like to know, could you guys give us just a sense of actually how much data has been pouring in and will continue to pour in, and exactly how long it's going to take you guys to go through all this, to actually figure out what exactly you've got and kind of what you can learn from it?
I'll give you one number. We've been observing since the 5th of September, and we will continue observing until Thanksgiving. From the 1st of October until we did our last maneuver a couple of days ago, one of the three instruments has delivered 23,000 images to the ground. The other camera has delivered fewer. The spectrometer has delivered a comparable amount of data. And that's just over approximately 1 month of the entire encounter that lasts 2 2/3 months.
The total number of images that we plan to bring down to the ground by the time we finish all the observations is approximately 120,000.
All right, I'm going to check one more time here in Von Karman. Yes, we do have a question. Wait for a microphone. Over here.
All right, one quick question. Where is the rotational pole in the image that we're looking at right here?
Great question. When you figure it out, please tell us.
And
there
then
is one.
It almost certainly goes through the short axis, but whether it's going this way or this way, we don't really know yet.
Okay, and then a more detailed question. I'm really, really struck by the bouldery nature of this thing and how similar that looks to Itokawa, the tiny asteroid visited by Hayabusa. And I'm wondering if people think that really tiny solar system objects are more bouldery or if it's just a coincidence.
Well, I wouldn't use the word boulder yet, because boulder implies rocks. And Itokawa is probably rocks, and it's got dominated by ejecta processes from impacts. This is very different. And I honestly can't say exactly what we called clumps were. There's a reason we chose a nice vague word, but it's not consolidated rock for sure.
Cool.
So, putting them together, well, yeah, very different processes. But they all have very little gravity, and that's something that's in common and is probably telling us dominating the way they're behaving.
All right, I think that takes care of all the questions here in the Von Karman Auditorium and on the phone lines. We want to thank you so much for joining us. It's been a wonderful day here at NASA's Jet Propulsion Laboratory. We're going to end the briefing with the replay of all the videos and images that you've seen during this news briefing. Thank you so much. Bye-bye.